This video is about area between the curves. Recall that integral can represent the area between f of x and the x-axis. Also, any area below the x-axis is considered negative. Any area above the x-axis is considered positive. A few things you'll have to keep in mind if you have y as a function of x or x as a function of y. You'll also have to realize which one is a top curve, which one is a bottom curve, and you also need to find points of intersections of those two curves or three curves or four curves, whatever you're dealing with. Okay, so the first formula, we're going to look at a simple example. Area under f of x, where f of x is greater than or equal to 0, for an example like this. Area is integral a to b f of x dx. So this is the area between the curve and the x-axis. That's the integral of f of x dx. Accumulated area between the x-axis and the curve f of x over the interval a to b, where a and b are the x values. How do we find area between the two curves or more than two curves? We can find the area under the top curve and subtract the area under the bottom curve from it. That would give us, the difference would give us the area between two curves. Okay, so it's important to realize over the interval which curve is on the top, which curve is on the bottom. Notice that f of x greater than or equal to g of x on the interval AB. So f of x is the top curve, g of x is the bottom curve. The formula for the area between f of x and g of x is integral a to b f of x minus g of x dx. So again, be careful which curve is on the top, which curve is on the bottom. If you don't have that correct, you would not have the correct area. You'd have the opposite. Okay, what happens if one curve is below x-axis and the other curve is above x-axis? It still works out as the area below the x-axis is negative, and when we subtract it, it ends up adding the total area. So here's an example. If you have a curve above x-axis, one below, when you're going to subtract, the two negatives will become positive, and we end up adding the areas. So that is okay. Here are the steps. The first step is sketch the graphs, if anything, just to see what it looks like. Actually, this step can be missed. You don't have to sketch the graph, but it makes your life easier if you sketch the graph. If you don't want to sketch the graph, the main thing you need to know is which curve is on the top, which curve is on the bottom, and the points of intersection. You can do that by plugging different x values over the interval. Whichever gives you higher y value, that is the top curve. Whichever gives you lower y value is the bottom curve. Step 2 is identify the top and bottom function. If they switch, find out where they switch, because sometimes they will switch. The top curve will become the bottom curve, and bottom curve will become the top curve at a particular integral. Find the limits of integration. Limits of integration, if y is a function of x, they will be our x values, and you can find them by setting the two curves equal to each other. If you have x is a function of y, then we would have to still set them equal to each other, and our limits of integration would be the two y values in that case. Okay, so set up the integral and evaluate. Here is the formula we should keep in mind. Okay, top function minus the bottom function dx, integral from a to b. The point where two graphs intersect, the x coordinates will be the limits of integration. We are first considering the y as a function of x case. Okay, so here's the first problem that we're going to look at. Again, y equals x squared minus 4 and g of x equals x plus 2. The very first thing I want to do is I want to graph this function. Again, I don't have to have exact graph, but a few main things I'm looking for is where does this graph touch the x-axis? I know it's a parabola opening up, and I also know it's touching the x-axis at two different spots. It's touching the x-axis at -2 and +2. And the y value is -4. This information I can just tell by looking at, if I plug x as 0, the y is -4. And if I plug y as 0 and factor that polynomial, then x comes out to be positive and negative 2. So those are the two x-intercepts. So here's my f of x graph. Now I need to graph my g of x, which is y equals x plus 2. I'm sure you do know that g of x and f of x is same thing as y. They are the same things. So y equals x plus 2 is line starts at 2, go up 1 over 1. Where does it meet the x-axis? Well, go up 1 and over 1. It is going to meet the y-axis at 2, but where does it meet the x-axis? We can plug y as 0 to find out where does it meet the x-axis. If I plug y as 0, then I can tell that it meets the x-axis at negative 2. Okay, so here's my graph, and here's the area between the curves that we're looking for. Area between two curves we're looking for. Okay, cool. So I do need to find the points of intersection. After I graph, I want to find points of intersection. I can clearly see I do have a top curve and a bottom curve. To find points of intersection, I'm going to set the two curves equal to each other. So this is my g of x. The f of x is a bottom curve. G of x is a top curve in this case. So let's go ahead and set these two to equal to each other. X squared minus 4 equal to x plus 2. Let's solve, bring everything to one side. And it's a quadratic equation. X minus 3, x plus, nope, 2 equal to 0. Because negative 3 times 2 is negative 6. Negative 3 plus 2 is negative 1. So factors work out. I get x equals 3 and negative 2. All right, so that means the point of intersection is x equals 3 and negative 2. Okay, so that's all I wanted from here. I'm ready to set up my integral. I'm going to go from negative 2 to 3. Top curve was g of x minus the bottom curve was f of x dx. Okay, so they don't switch spots, so that's good. Again, negative 2 to 3, g of x was x plus 2. Do not forget the parentheses, because if you don't put parentheses, you may forget to distribute the negative sign inside the parentheses. That comes out to be negative 2 to 3, x plus 2 minus x squared plus 4 dx. Let's see what does that. Let's simplify it a little. There are like terms. We have negative x squared plus x plus 6 dx. And when I do the integration, we have negative x to the third over 3. That is a 3 here. Let me make it neater. Negative x to the third over 3 plus x squared over 2 plus 6x. And the bounds are from negative 2 to 3. So I'm going to go ahead and plug all the bounds here. Plug the 3 in there for x, and then subtract by plugging negative 2 in there. It's going to come out to be 125 over 6. Okay, I'm not going to spend too much time on the definite integral here. You should have practiced that enough. So moving on to, that is the area between the two curves, 125 divided by 6. Okay, it's okay to leave it as a fraction. There's no units attached, so no need to worry about the units. Here's another example, example number 2 for area between the curves. I am looking at a cos x and a sin x graph over pi over 4 to 5 pi over 4. Okay, very important to make the neat graph first. All right, so I'm going to do the sin x graph first. This is 2 pi, this is pi. So the sin x graph does start at 0, go to 1 and negative 1, and comes back here. I may not need all of the graph, but straight lines. Sorry, let me redraw it over here. All right. There's pi over here. All right. Cosine graph starts at 1 and goes to pi exactly in the middle, and then comes back to 1. All right, so we're looking at the point of intersection here. Where is the sine value and cosine value equal? They are equal at pi over 4, and they're also equal at 5 pi over 4, because in fourth quadrant they are both positive again. Pi over 4 and 5 pi over 4. In first quadrant they both are the same, and in fourth quadrant they both are the same, they both are negative. So we're looking at this shaded region that's in between these two curves over the interval of pi over 4 and 5 pi over 4. The whole reason why I did the graph is just to find out which curve is on the top and which curve is on the bottom. Looks like sine x is on the top and cosine x is on the bottom. So when I set up my integral, I'm going to be doing pi over 4 to 5 pi over 4 sine x minus cos x dx. All right, so let's go ahead and do the integration. What's the integral of sine x? Integral of sine x is negative cos x. Integral of cos x is positive sine x, but that negative comes down. And we have pi over 4 to 5 pi over 4 as my interval. Now it's just a matter of plugging the values in. So I'm going to do negative cosine 5 pi over 4 minus sine 5 pi over 4. And I'm going to subtract the lower bound values. When I do the subtraction, they're actually going to get added. So both of them will actually become positive here. And I'm going to go ahead and plug the values now. So this is going to be, this is negative, and the value in itself is negative, so that would make it positive. There's negatives here, that would make it positive. Root 2 over 2 again, plus root 2 over 2, plus root 2 over 2. Okay, so the negative and a negative becomes a positive and a positive. So here we are left with root 2 over 2 plus root 2 over 2. Okay. 4 root 2 over 2, which turns out to be 2 root 2. And again, there's no units, so no need to worry about writing the units in there, but we are okay with leaving our answer without any units. 2 root 2 is the area between the two curves. Okay, so next example number 3. Find the area between the curves x squared minus 5x minus 7 and g of x is x minus 12 over this interval. If they didn't give me the interval, that's fine, but if they do, then I need to keep that interval in mind. Let's go ahead and start graphing. You can always take help from Desmos for graphing if you need to graph the function really quick and you don't remember how to, but you should brush up on your skills for graphing as well. So I'm just thinking about, this is not factorable. That means it's a parabola that opens up. It touches the y-axis at negative 7. I see that. So I don't know exactly. I use Desmos, and I think it's somewhat like this is the graph for this function. And that's my f of x. Now I'm going to graph my g of x function. G of x is a straight line, x minus 12. Where does it touch the x-axis? It touches the x-axis at positive 12, which is somewhere here. And it touches the y-axis at, if I plug, it touches the y-axis at negative 12. So it's a line that looks something like this. Okay. Now, the interval over which we are looking for the area is between negative between negative 2 to 5. So let's say negative 2 is about here. Sorry about the not so pretty picture, but we get the point. So we have some area, some region here. I do want to find out where do these two graphs intersect. So x squared minus 5x minus 7 equals x minus 12 to find the point of intersection points. Okay, bring everything to one side, minus 6x. When we add 12 over here would be plus 5 equal to 0. So I get x minus 5. It's factorable equation, x minus 1 equal to 0, x equals 1 and 5. So here we are. So it does meet at x equals 5. That's the point. And x equals 1 is also a point where they intersect. But why am I going all the way on the -2? Because of the interval that was given to me. Because I want to find the area over this interval in between two curves. Now the thing about this problem is your top and bottom curves are switching. If you look between -2 to 1 over the x-axis, interval -2 to 1, you have your parabola on the top and the line on the bottom. And if you look from 1 to 5, you have the line on the top and parabola on the bottom. So we'll have to set up two separate integrals here. Okay, so between -2 to 1, we got the parabola on the top, which is f of x minus g of x dx. And then plus, we have more area from 1 to 5. We actually have g of x on the top because g of x is the line, remember, the purple line? G of x minus f of x dx. All right, let's go ahead and plug the function values and simplify our area under the two curves. I should have given myself more space, but if I don't, I would just not simplify the integrals, okay? If I don't have enough space, I would just not simplify the integrals. So here we have the parabola on the top, x squared minus 5x minus 7, and then subtract the line from it. Do not forget, negative sign will get distributed, okay? Between 1 to 5, I do have the line on the top, which is x minus 12. Again, you're going to distribute the negative sign. So we're going to have negative x squared plus 5x plus 7 dx. Okay. And from here, go ahead and simplify. I can use the integral calculator and plug these two integrals, definite integrals, into the calculator. It should come out to be 113 divided by 3. Okay. And that's the area between these two curves. So graphing helps you give an idea which curve is on the top, which curve is on the bottom, how do they compare to each other, and it also gives you estimate where do they intersect. Okay. But you can also find points of intersection by plugging the curves equal to each other to know exact points of intersection, because you need them for your boundaries for upper and lower bound for the integral. Okay. Next example, find the area between the curves. So we have e to the power x and e to the power 2x. Okay, we do know that e to the power x looks something like this. And we also know e to the power 2x, as they all pass through the 0.01 exponential functions. So this is e to the power x, e to the power 2x. As your exponent is higher, your graph is going to be more and more steeper. They're both exponential functions. And we're looking we're looking area between these two curves over 0 to 1. So that means we are looking for this shaded region between the two graphs. Okay, the only thing I needed from here is which curve is on the top, which curve is on the bottom. Looks like e to the power 2x is on the top. You could also try plugging in any x values and see which one gives you the higher y value to decide which is the top curve and which is the bottom curve. Okay, so here we are. Set up the integral. The bounds will be 0 to 1. The x equals 0 is here. X equals 1 is here. 0 to 1, the top curve is e to the power 2x. The bottom curve is e to the power x dx. This integral is not too bad. We could just split it into two integrals or just do the integral of pieces. Remember, when you do integral of e to the power 2x, you have to divide by 2 minus integral of e to the power x is e to the power x. and we're going from 0 to 1. Okay, let's go ahead and plug the values in. We have 1/2 e to the second power minus e minus 1/2 e to the 0 power minus e to the 0 power. Okay, that simplifies to 1/2 e squared minus e, and e to the 0 power is 1, so this is 1. This would become plus 1, right? So we have minus 1/2 times 1 is just negative 1/2, and this would be minus 1 as well. Yep, this would be negative 1/2 e to the power 0 is 1 minus 1. That would be negative 3 over 2. 1/2 e squared minus e minus 3 over 2. And that's the area between these two curves. All right, so next problem. Now we're looking at area between three curves. Well, again, graphing will help us. If you draw the picture, again, you can use Desmos to do the graph for you. Makes your life a little bit easier. You do need to know the top bottom curves. So either use Desmos or do manually graph. Make sure you're keeping a log of your work. Write every step down on a neat, organized manner on a piece of paper. So here I have three different lines. X plus y equals 4, x minus y equals 0, y plus 3x equals 4. I'm going to put them in a little bit neater order. I'm going to call this f of x. I'm going to call this g of x. I'm going to call this h of x. I'm going to write them in the function form. Okay, I'm going to isolate the y. So f of x is actually, I can say y is equal to 4 minus x. That can be my f of x. And g of x, if I isolate the y, it is just y equal to x. And h of x, if I isolate the y, that would be just, I can say negative 3x plus 4 is equal to h of x. Okay, so these are my all three functions written in the form of f of x as a function of x. Okay. They were in the equation form. I wrote them in the function form. All right, so let's go ahead and graph these three lines. Where does the first line meet the f of x meets the x-axis? It will meet the x-axis at x equals 4. It will meet the y-axis at 4. So the first line f of x would be something like that. And the second line would be something like this, going this way. And the third line is something like this. Y is equal to x would be something like this. So we have f of x. Maybe I should use different colors. F of x here. And g of x is this line. And h of x is this line. Okay, let's find the points of intersection. Points of intersection. So I have three different curves. I'm not going to set all three to equal to each other. First, I want to find points of intersection of f of x and h of x. So I'm going to be dealing with 4 minus x equal to negative 3x plus 4. And that is going to give me x is equal to 0. And when x is 0, y will be 4. So they meet at 0, 4. Those two lines meet at x equals 0. At 0, 4, these two lines meet. F of x and h of x meet at these 2 points, these two lines. Okay, I'm going to erase this side because I guess I don't need this side. So next I want to find points of intersection of which two curves. We can look at h of x and g of x. Okay, h of x and g of x. H of x is negative 3x plus 4. G of x is just y equal to x. And when I solve this, I get 4 is equal to 4x, x is equal to 1. We can plug x equals 1 in any of these two curves, and we see their point of intersection is 1, 1. H of x and g of x meet at 1, 1. So this is a 1, 1 point where these two meet. Next, I need the points of intersection of, I think I haven't looked at, I did h of x, g of x, I did f of x, h of x. So h of x and g of x and f of x. Those are the two that I have not found the points of intersection, f of x and g of x. Okay, so f of x and g of x. All right, so f of x and g of x, I'm looking for the points of intersection. Let's plug them to equal to each other. 4 minus x equals x. Let's go ahead and solve it. We get 2x equals 4, x equals 2. So 2, 2 is their point of intersection. So that means this point is 2 and 2. G of x and f of x meet at 2, 2. All right, good. That was a lot of work. Now, since we found the points of intersection, I'm going to delete the work for points of intersection, and I'm going to work on setting up the integrals, okay? So we can kind of divide it into two regions. We can look between, so we can keep the purple region integral, and then we can set up the integral for the pink region, okay? So erase the work for points of intersection. We already have the points of intersection. All right, let's go ahead and set up the integrals now. I need to do, okay, from 0 to 1 and then from 1 to 2, I'm going to have two different regions. From 0 to 1, which curve is on the top? F of x is on the top, h of x is on the bottom. F of x was 4 minus x minus the h of x was negative 3x plus 4 dx. And now between 1 to 2, which curve is on the top? We have f of x on the top, which is 4 minus x, minus the g of x is on the bottom, which would be x. Okay, now we just need to evaluate these two integrals, simplify, open up the parentheses, and I'm going to have 0 to 1, 2x dx. When I open the parentheses, combine the like terms, 1 to 2, 4 minus 2x dx. Okay, so that's 2x squared divided by 2 from 0 to 1. The bounds are 0 to 1. 2x squared divided by 2 from 0 to 1 plus 4x minus 2x squared divided by 2. The bounds are 1 to 2. 1 to 2. And I'm just going to use a calculator for that. It is going to come out to be 2 when you add these two areas. Okay, main focus in this video is not how to evaluate definite integrals. That's something you've learned in Math 1A. Should have done many problems. So I'm not spending time on evaluating the definite integrals, but you will need to do that for the homework as well. And I would recommend that don't use a calculator, so that you know how to evaluate definite integral. At least in the beginning of the semester, you want to make sure you can handle evaluating the integral. Definite integral, just plugging the bounds in. Okay, so next example, what if we are given y as, oh, I meant to say x as a function of y. This is a typo, so please correct it. X as a function of y. So this is not correct. What if we are given x as a function of y? Okay, in that case, what can we do is we would have the c and d will be the y values, and we can have a right function and a left function and dy. Okay, let's go ahead and look at an example from it. Again, please make that correction in your supplement. It's not y as a function of x. You should say x as a function of y. All right. Find the area enclosed to the right of x equals y squared minus 5 and left of 3 minus y squared. All right, so we are dealing with two parabolas. This parabola, the y squared minus 5, this parabola opens to the right, and 3 minus y squared, because it's got a negative y squared, this one opens towards the left. We do want to kind of think about where do they touch the x-axis. Where does this parabola touch the x-axis when the y is 0? It touches the x-axis at negative 5. And maybe I should think about where does it touch the y-axis as well. But that one, if I want to find out where does it touch the y-axis, would be square root plus minus square root of 5. The second parabola, I know it opens towards the right because it touches the x-axis at positive 3. This one touches at negative 5. Let's also find out the points of intersection by setting the curves equal to each other. So we want to find points of intersection to give me better picture of the graph. Okay, so that would turn out to be 2y squared equals 8. Y squared equals 4. Y equals plus minus 2. So they do intersect at y equals positive 2 and y equals negative 2. So that's positive 2 and that's negative 2 here. And I'm actually looking for this area that's in between the two curves. All right, let's go ahead and set up our integral. So we want the right curve minus the left curve, and the bounds would be the y values now. So this is a positive 2, and this one is a negative 2. So the bounds would be negative 2 to 2, the right function. Which one was the right function? It's actually very helpful if you write with the curve. This is 3 minus y squared, and this one is y squared minus 5. The right function is 3 minus y squared, minus the left function is y squared minus 5 dy. Okay, so we have negative 2 to 2, 3 minus y squared minus, this doesn't look like y squared, so make sure it is y squared, plus 5 dy. Simplify, which is negative 2 to 2, 8 minus 2y squared dy. And at this point, we are really just simplifying the definite integral. So this would come out to be 8y minus 2y to the third divided by 3. The bounds are negative 2 to 2, and it's going to come out to be 64 divided by 3. When you plug the values in and simplify, it would be 64 divided by 3. Okay, that's going to be the area between the two curves. Okay. All right, next example, we're going to look at another example of area between the curves. Find the area between the curves. Y equals x minus 1, y squared equals 2x plus 6. Okay. All right, y squared equals 2x plus 6 is a parabola. And this is a parabola that opens towards the right. Okay. X minus 1 is a line. So let's go ahead and first find points of intersection. That's very helpful if you find the points of intersection first. Okay. To find the points of intersection, I need to plug the curves equal to each other. But again, since this is y as a function of x, I'm going to x is a function of y here because we have y squared equals 2x. We can write them actually either way, but because we have y squared equals 2x plus 6, I'm going to say this would be this is going to be x equals y plus 1, and this would be x equals 1/2 y squared minus 6 if I isolate the x from both of them. Okay. I wrote x as a function of y in these cases because they were the right and the left kind of curves to me. So 1/2 y squared minus 6 equal to y plus 1. Let us simplify. This gives me 2y plus 2 equal y squared minus 6, y squared minus 2y minus 8 equal to 0, y minus 4, y plus 2 equal to 0, y equals 4 and negative 2. Okay, so my points of intersection are 4 and negative 2. And let's go ahead and see where does this is a parabola. You can use Desmos to graph, or you can use the skills you learned in previous courses to graph. Y squared is equal to 2x plus 6. That's the parabola here. And then they meet at 4 and negative 2. The line is starting at negative 1, go up 1. Okay, this is how the line is going to look like. All right, I'm just going to make that. All right, so this is 4. This is negative 2. Okay. And it doesn't matter where does the line cross the x-axis, because, or the y-axis, we don't need that. So this point is negative 2 here, point of intersection, and the other point of intersection is 4. So this piece is really, really important. And we know it touches the x-axis at negative 4. You can plug y equal to 0 and solve. That's how you can tell that this is going to touch the x-axis at negative 4. All right, let's go ahead and set up our integral. We're going to do the right curve minus the left curve. It's going to be an integral with dy at the end. Now we're going to do the boundaries as the y values as well. So y from negative 2. Okay, hold on. There's a correction. The points of intersection we got are not the x values, they are the y values. So I'm going to correct that, please. I apologize. I'm going to correct myself. The points of intersection we just found are the y values, okay, not the x values. All right, so negative 2 to 4 on the y-axis. The right curve, I'm going to write x as a function of y plus 1 minus the left curve. If I distribute the 2 inside, it's that times dy there for the operator. And when you simplify this integral, you can use a calculator or however you want to. Turns out to be 18. Okay. Next problem, find the area enclosed by y equals natural log of x over x and y equals natural log of x squared divided by x. Okay, so a little bit of work here. Plotting these points, graphing these equations is not very obvious because they're not one of our parent functions that we have learned. I want to start by finding points of intersection, and you can use Desmos to graph, or you can just plot points and graph if you want to. To find points of intersection, I'm going to set the two curves equal to each other. I'm going to bring everything on one side. Actually, I'll take everything to right hand side. I'm going to bring everything to one side. So we have natural log of x squared over x minus natural log of x over x, which turns out to be, I can pull out a natural log of x over x and 1 minus, I would have 0 on the other side. I was trying to do the next step there too. Now natural log of x over x can be pulled out, and then we have inside, we would have natural log of x minus 1 is equal to 0. Okay, now if I plug each factor equal to 0, natural log of x over x equal to 0, natural log of x minus 1 is equal to 0. This gives me natural log of x equal to 1, and this gives me natural log of x equal to 0, because if I multiply with the x, it's gone. Okay, now natural log of x equal to 1, that means x is equal to e, and natural log of x is equal to 0, that means e to the power 0. This means x is equal to 1, right? So my points of intersection are x equals e and x equals 1. That's good. I found my points of intersection there. So if I try to graph now, the two functions are going to look something like this, and we want the area in between the two curves. Okay, the top curve is natural log of x over x. The bottom curve is natural log of x squared over x. And this is 1 and this is e. Okay. All right, so 1 and e here. Let's go ahead and set up our integral. We have a top curve, we have a bottom curve, we have the boundaries for integration from 1 to e. Natural log of x over x minus natural log of x squared over x dx. And again, you can use Desmos however you want to simplify. This would be integrate natural log of x over x. You can do the u substitution there. In both of these, you would need the u substitution because derivative of natural log of x is 1 over x dx. So you would just have u du minus u squared du. Okay, so use the u substitution in these. I'm kind of running out of the space. So I would just use an integral calculator, and it turns out to be 1 over 6 is the area between the two curves. Okay, let's see if there's any more examples. That's all for the examples for area between two curves.